Problem 18 asks us to solve some equations. For the equation in part A, I can start by distributing the 5 on the left-hand side to remove those parentheses. I get 5x minus 20. And on the right-hand side, in a similar way, I can distribute the minus 3. And the right-hand side then becomes 2x minus 24 minus 3x. And now I can add 20 to both sides and combine the like terms, 2x and minus 3x. This will give me 5x equals negative x minus 4. Next up, I can add x to both sides to get 6x equals negative 4. And finally, dividing by 6, I get x equals negative 4 over 6, which simplifies to 2/3, negative 2/3. So our solution is x equals negative 2/3. Of course, as with any equation, I can check my work by taking that number and plugging it back in for x, and seeing that the left side and the right side evaluate to the same amount. The equation in part B is a little more complex. We have a square root involved in this equation. I want to start by subtracting 5 from both sides, which gives me the square root of 3m minus 4 equals 3. And now the next thing I can do, to eliminate the square root, I can square both sides of the equation. So this is a balanced thing I can do to both sides of the equation. It cancels out the square root and gives me 3m minus 4 on the left-hand side and 9 on the right-hand side, 3 squared. I can then add 4 to both sides to get 3m equals 13. And dividing by 3, I get m equals 13 over 3. The equation in part C is a quadratic equation, but it's not in standard form. So let me start by putting that equation into standard form. I get a squared plus 3a minus 4 equals 0. And now what I'd like to do is factor the left-hand side. So I want to find two numbers that multiply to equal negative 4 and add to equal positive 3. Of course, the two numbers that work are positive 4 and negative 1. So my trinomial factors as a plus 4 and a minus 1. And now I'm going to use an important idea in algebra called the principle of zero products. If I have two things that multiply together and equal 0, so if I have a factored expression equal to 0, the only way that that can be true is if either the first factor, in this case x, equals 0, or y equals 0. So what I know from this factored expression set equal to 0 is that either a plus 4 equals 0 or a minus 1 equals 0. If the first equation is true, we get that a equals negative 4 by subtracting 4 from both sides. And if the second equation is true, I get that a equals 1. And so either one of those equations can be true to make the initial equation true, so we get two solutions. My solution set is negative 4 or positive 1. And since those two solutions are pretty friendly, I'm going to take a moment to check that they work. If I plug negative 4 in for a, I get negative 4 squared, which is positive 16, plus 3 times negative 4, which is negative 12, and combining those equals 4. On the other hand, if a equals 1, I get 1 squared, which is 1, plus 3 times 1, which is 3, which also equals 4. So both of these solutions work. Part D is also a quadratic equation, but it's a bit more complicated. So let's work through the process and see what we can come up with. If I put it into standard form, I get 3y squared minus 7y minus 40 equals 0. But now this time to factor, I'm going to use the AC method. If I multiply 3 and negative 40, I get negative 120. And now what I want to find is a factor pair that multiplies to equal negative 120 and adds to equal negative 7. So one way to think through this process is to list all possibilities. I want the larger number to be negative, so I get a negative result when I add them together. So starting with 1 and 120, I could take 1 and negative 120, 2 and negative 60, 3 and negative 40. There's a whole lot of numbers in this list. 4 and negative 30, 5 and negative 24, 6 and negative 20, and 8 and negative 15, and there we have it. That's the pair that's going to work. 8 and negative 15 add to negative 7. So I can rewrite my equation as 3y minus 15y, 3y squared I should say, minus 15y plus 8y minus 40 equals 0. And because I found that special factor pair, 8 and negative 15, I can factor the left-hand side by grouping. I can factor out a 3y from the first group, and it leaves behind y minus 5. And I can factor out an 8 from the second group, and it also leaves behind y minus 5. So my factorization is 3y plus 8 times y minus 5. And now using the principle of zero products like we did in the previous exercise, I know that my solution is going to come from setting 3y plus 8 equal to 0 and y minus 5 equal to 0. That first equation gives me a solution of y equals negative 8/3. And the second, of course, gives us a solution of y equals 5. So my solution set, putting it in curly braces, is positive 5 and negative 8/3. And finally, our last example, part E, is an absolute value equation. So what that means is that whatever this expression is, it's going to become the positive value of that number. So the two numbers that I can put inside the absolute value to get a positive 5 would be positive 5 or negative 5. So I can create two simpler equations. Either n plus 2 just equals 5. The absolute value would then turn this expression into positive 5. Or n plus 2 could equal negative 5. And then the absolute value would turn that into positive 5. So from the first equation, I can see that n would equal 3. And from the second equation, I can see n would equal negative 7. And we could plug those in to make sure that it made sense. Of course, 3 plus 2 is 5. The absolute value of that is 5. Negative 7 plus 2 is negative 5, and the absolute value of that is 5. So both of these solutions work, and I can write the combined solution set in curly braces as 3 and negative 7. So let me quickly summarize our solutions here. For part A, we have x equals negative 2/3. For part B, we have m equals 13/3. Part C has two solutions, negative 4 and positive 1. Part D also has two solutions, 5 and negative 8/3. And part E has two solutions as well, 3 and negative 7.